Welcome. Today we'll be discussing intelligence analysis and ontology engineering from a top-down perspective. Broadly speaking, first I'll discuss big data, the problems associated with it, and the intelligence cycle, and then ontology engineering and how it may address, to some extent, some of the problems that arise. So big data, big problems. What does this mean? So there is a lot of data, as you know, comes in various formats. It's hard to extract certain value. It's hard to get like organize inconsistencies and uncertainties around it, or at least sort them out. And it comes in at a high speed. So as of 2022, there has been over 147 zettabytes of data stored already, just from various like Internet of Things devices, from like login screens, etc. Like all this data is being stored in various places, zettabytes. So what is that? It almost sounds made up. Just to put this into perspective, so a 50 megabyte connection will allow you in the comfort of your home to stream a 4K video. In fact, it will allow you and several members of your family to simultaneously stream 4K videos. So at 50 megabytes per second, though, it would take you 634,196 years to stream 1 zettabyte of data. Now for 147, it would take you over 93 million years to stream. So quite a bit of data. There's also increasing the amount of data is increasing almost exponentially over the years. So 0.4 zettabytes have been stored per day. That should say actually as of 2024. That's a significant increase over previous years, and it looks like it's just going to continue increasing till we get out of the zetas and whatever comes next. So this data is stored or obtained from places where it's sometimes trustworthy and sometimes not, like academic research. Some of that is vettable, some of that is trustworthy. Twitter, not so much, or X if you prefer that. It also comes in various standards like XML and Turtle, the TTL, and then JSON LD, etc. So different formats, different sources, different trustworthiness associated with them, and different hurdles to integrating them. Also, conflicts invariably emerge sometimes between trustworthy sources, but also between untrustworthy sources, as you can imagine. And it's hard to sort out the inconsistencies and the uncertainty from the data, especially at this such massive data coming in at such a high velocity. And then, just as important as all the above, being able to extract useful information that is generated at such a fast clip is, to say, just in a word, quite challenging. So how do we address this? Well, intelligence analysts have some strategies. They weren't designed to address this big data problem, but they actually have some benefits that go some ways in addressing some of these big data issues that we're encountering here. So the intelligence cycle is something that's often referred to in these circles, which is a systematic process used by agencies engaged in intelligence activities that outline stages through which raw data is transformed into intelligence. Now, leveraging the intelligence cycle at least partially addresses some aspects of issues arising from these big data problems. So before it's preliminary, though, I just want to point out, so intelligence analysis is often conducted within agencies. I'll call them epistemic communities, which is just to say they're communities that share normative beliefs about the purposes of their actions, beliefs based on experiences from investigating central problems in their domain, standards for accuracy for analyses in their field of expertise, and common community goals. And you can see some icons from various intelligence organizations across the world. I think it's plausible to classify them all as epistemic communities. They all exhibit these sorts of characteristics. And this is important, especially as we get into the first part, or roughly speaking, one of the initial stages of the intelligence cycle, which is planning and direction. So this is critical to the success of any intelligence program, and it's the step in which decision makers define objectives and set priorities for what needs to be known, and thereby, in doing so, providing standards against which data can be judged as valuable or not. And this essentially sets down the framework out of all the morass and all like the boom and buzz of data coming in. Like, it sets down the parameters under which analysts will seek out and sort through what's valuable, because it gives them kind of a North Star for identifying such things. Now, that leads naturally into the collection process, which helps determine where and how to conduct data acquisition and information gathering, and it often involves standards for acquiring large amounts of data from diverse sources at high speeds in different formats, like structured, unstructured, multimedia, etc. And in doing so, provides some strategies for addressing like the sheer volume of data out there, especially in combination with the planning and direction aspect, but also strategies for getting clear, or at least standardizing the variety of data that is acquired, whether it's like in different formats or whatnot. Again, so then this is taken and processed. You can think of this as like just cleaning the data. Anybody who's worked with raw data knows it's not very clean. They're often like question marks in cells and whatnot, or like blank information, missing info. You got to clean this if you're going to process or through processing if you're going to analyze it. And this step often involves converting raw data into usable formats for various tools that agents or analysts have. Also evaluating data for relevance, just making sure that it aligns with the goals laid down by the planning and direction stage. Also removing irrelevant data and cleaning whatever remains to improve the quality. These steps help address some of the issues that come up through a variety, namely the variety of standards that you might encounter in the wild when you're doing the collection. But it also helps to get clear on the veracity, or make some headway towards veracity. So is this data relevant? Is it not relevant? We can do kind of a first pass and see, so we can sort, in doing so, sort through a bit more through the processing step and focus on the data that the analysts are interested in analyzing. So in that analysis step, a very, very robust step, this is the step in which the analysts think through relevance, accuracy, again, and completeness in satisfaction, or insofar as the data satisfies or may satisfy the original requirements. Now, this step produces actionable intelligence, or it aims to produce actionable intelligence by evaluating the data for accuracy and validity. An example of this would be agents or an analyst comparing satellite images to ground reports to verify the movement of some troops. If you get, for instance, satellite imagery that says troops are moving north and a lot of ground reports saying that troops are moving east, something's gone wrong. Sorting through what's gone wrong will help promote the accuracy of your data and help sort through what's good data, what's bad data. And this is the result of this, again, should be actionable intelligence. And in doing this, you get to you hopefully can see sort of eye towards veracity, or eye towards relevance, eye towards utility. And I understand the intelligence cycle is producing intelligence insofar as that data is valuable. Lastly here, but certainly not least, is the dissemination and feedback step, which is putting the data in the right format, or the intelligence at this point in the right format, in the right hands at the right time, and through the right media. And this promotes timely delivering of intelligence to decision makers as they need it, with the cycle ultimately acting as a filter to extract something valuable from the massive flood of incoming data. In that respect, helps address velocity, like the speed, all of this data coming in rapidly, how do you sort through it? You can think of this as a sieve to help get you the valuable information out of what's coming in. So, looks like we've addressed through the intelligence cycle several of the issues that arise from big data, right? Great. Give ourselves a round of applause, but not that quickly. There are also some issues that we have to address. I wish things worked so cleanly, but unfortunately there are blockers that get in the way. Let me back up then. So, an information silo is an information repository, management system, database, etc., the content of which cannot be integrated with that of other information repositories using computing strategies, or at least cannot easily be implemented, or at least they're not known strategies for integrating such things. Now, information silos occur all over the place. If you have a data set over here, in company A, and you have a data set in company B, and they're both, say, I don't know, about time series or automobiles or something like that, if they are not coded with similar standards, if they don't use similar semantics, if they don't have any kind of connection between them, you can't easily integrate that information. And this doesn't just happen across organizations, like companies, different rival companies perhaps occupying the same domain. It also happens inside organizations, especially large organizations, like for instance government organizations that acquire large amounts of data and often find themselves in the situation where the right hand doesn't know what the left hand is doing, and there's a significant amount of data just sitting out there about the same domain that data in other parts of the organization is about, but cannot just be easily integrated owing to different formats, as I was saying. Now, information silos can manifest in organizations for a variety of reasons. In some cases, groups just don't realize the given information repository exists. So Simple example here, you can have like an organization that is modeling tomatoes. You can have another part of that very same organization that is modeling like seasonal growth patterns or something. They happen to end up talking quite a bit about tomatoes. Now, if the organization is large enough, the larger it is, I should say, the more likely it becomes that one side of the company can be entirely ignorant of what the other side is modeling. Like this happens all the time. I've been in rooms with well-intentioned representatives from the same organization who have found themselves in just this sort of situation. One group will say, hey, if only we had data about topic D, and then another part of the room you hear off in the corner behind you as you're looking at this person who's wishing they had data about D, somebody say, we do. And then all of a sudden, that ignorance is absolved, but nevertheless, there are these two information silos that were born out of it, and they've been like operating independently of one another, gathering data in their own formats and own standards, even about the same topic or topics of interest to other groups without awareness across the enterprise. So these things happen quite frequently, and again, the larger the company, larger organization, the more likely it seems that these things tend to happen. So it could also be the case that groups are not ignorant of data sets or information repositories within or without their organization, but they just don't have the appropriate permissions to access that information. Now, examples here, sort of ignorance and also inaccessibility, but back to one of the cases that sort of motivated the beginning of the class, 9/11, right? Recall that I was mentioning resulting investigations after 9/11 revealed that U.S. intelligence agencies knew al-Qaeda was mobilizing, but that information was not shared widely across intelligence agencies in the U.S. In some cases, there was awareness that this group or that group might have this sort of information, but there were accessibility issues, namely due to compartmentalization of intelligence. Like maybe some groups who surmised that other agencies in the U.S. government had certain information that might be relevant. To get access to that, they may have needed to make a case that they had a need to know that information, and sometimes that case is not exactly easy to make. Other times, and this is what I'm pointing to here, there's just sort of an ignorance going on. Like at the time, the NSA considered itself an intelligence curator. If an agency had asked whether, for instance, al-Qaeda was mobilizing, they would have confirmed, but few people knew to ask. Other ways in which silos manifest, just infeasibility. Some groups might not have the appropriate technology to access, and I think as more and more agencies are like becoming aware of siloing and the problems associated with it in their organizations, this is becoming more and more the issue. Appropriate technology has not been developed, or at least not implemented, certainly not at enterprise level across the organization, to bring silos together. And this is one of the things that ontology engineering aims at addressing, and it's one of the things that we'll be focusing on a lot here. But before moving to that, I just want to point out sometimes folks just don't care about integrating with other repositories. And now, while I think there are, in some cases, good reasons for organizations or groups to not want to integrate their data with others, like other repositories, or even think about integrating their data with other data, I think for the most part, those kind of like understandable and defensible cases are less common than what is more common, which is one of these other scenarios. So I'll give you an example, though, of a reasonable case, or at least a defensible case, where you just might not want to integrate your information with that of others. So you can imagine, or hopefully it's not too hard to imagine, you say running an education center like a university. You have a lot of information about students, and you may not want, say, marketing executives to have access to that student data, because you might not trust those marketing agents. You might not trust what they might do with that data. So it makes sense that you would keep that data not integrated. Now, one of the things that we do in ontology engineering is we try to provide like a high-level connection across disparate data sets like this. But currently, because of the technological challenges between, say, not to mention the legal challenges and whatnot, but technological challenges exist between integrating like an educational data set or data set about students in an educational environment to, like, marketing data. even if you put the legal stuff aside, currently they're not like clear technological solutions. There's an infeasibility issue. And now I say insane, and I'm being a little tongue-in-cheek because there are examples of cases where you might not want to integrate data in one group with that of another. So think about like an education institution that has a lot of data about students, and they may want to keep that information separate from, say, marketing executives or marketing organizations that have data, nearby data that could be used or leveraged to sell things to students. And if they had more information about student profiles, certainly like the information that academic institutions obtain, they might use that to sell even harder to those students. It seems plausible to me, at least it's a little compelling, that an academic institution might want to block marketing agencies from having access to that. Of course, they do, right? Like there are laws in place that prevent this sort of things. But if you put the law stuff aside, even putting all of that aside, there's sort of like an infeasibility challenge going on here. Like there currently groups like most academic institutions, they don't have the technological connection. They don't have like a semantic bridge or like some way to get information over easily through using some computer strategies into the hands of marketing agents and incorporated in their data sets. And conversely, like marketing agencies can't just like import their information and like integrate it with that of or academic institutions for technological reasons. Now, one of the things that we try to do in ontology engineering is provide the kind of technological solutions that will allow those sorts of mappings to occur. And in that way, we want to address some of these silos. But I can imagine, it's not hard to imagine at least, that an academic institution might want to maintain that kind of natural technological barrier, even if like there are laws in place, like even in the off chance that like marketing agencies could just like violate the law. It seems plausible to me that they might want to maintain that natural technological barrier just in case. And I don't think of that as insane. I think that's a very defensible position. Unfortunately, when I'm using insane here about people who don't care about integrating with other repositories, I have a kind of a much more common sort of scenario in mind. And that's when groups who need to, say, move quickly when they're gathering data or organizing data or put it in their systems, they kind of like model the world as quickly as they can for given use cases. They don't think about how their data might connect with other data sets in the broader community, or like think about how they might future-proof data, so they don't have to come back and fix it and create a bunch of technical backlog and whatnot. They instead just trying to meet this sort of local needs quickly. What happens is they don't really care about integrating with other repositories or other sorts of information because that's not relevant to what they're being tasked to do or what they're, say, being paid to do. But unfortunately, the reason I call this insane is because oftentimes, and I'll end with an example in here to illustrate what I mean, but like oftentimes folks who are building locally find a need to have to come back and fix what they've done again and again and again, or just reinvent it again and again and again. And now, if you are, partial to the definition of insanity, which involves doing the same thing again and again and expecting different results, I think it's plausible to consider that sort of behavior at least coming close to being crazy. So that aside, costs associated with silos are significant. So in 2020, a report by NIST estimated the lack of interoperability across industrial data sets cost companies between 21 and 43 billion US dollars. That is a lot of money. And McKinsey estimated mid-sized companies spend about $20 to $50 million annually due to silos. And what are they spending the money on? They're spending money on groups in-house often, or maybe contracting groups out to connect data sets within their organization to other data sets. Now, there are various ways to do this. You could hire a bunch of computer programmers to just come in and write code to script these things together, integrate or provide solutions in that manner. That is probably the most common strategy that's pursued, unfortunately. The reason I say it's unfortunate, though, is because you have an n squared problem that arises. Anytime you have new data sets that are added in, you have to create mappings between them all if you want to integrate the data. Say you start with 2 data sets. right? You want to map one to the other. They were developed independently of each other. There's not like a common connections, but you want to integrate them. You're going to need a map between one to the other and the other to the one. So there are two mappings there. Now let's say you add in a third. How many mappings do you need to construct to integrate all three of those data sets? Well, 1, 2, 3, 4, 5, 6, right? You have to map one like A to B, if we call the first one A and the second one B, and the third data set C. You have map A to B and B to A. You have to map B to C and C to B, and then you have to map A to C and C to A. There's no royal road to the mapping. You have to do them all or literally every single time. You have to go in and write the mappings yourself, back and forth. Now, add a fourth data set, add a fifth, and what you get is an n squared issue where you have to construct you have to create n squared numbers of mappings for every n. What you get is an exponentially growing number of mappings that you have to produce to integrate all of this data. And that, again, doesn't sound very appealing to me. Vetting, filtering, processing, etc., to some extent address these big data problems, but the challenge of information silos threatens to undermine the virtues even of the intelligence cycle that we've been discussing. So unfortunately, information silos seem rather common among intelligence organizations and agencies that depend on them, and here's some of the issues that come up. So siloing results in data fragmentation and redundancy, and it undermines the consolidation of data. And so like the virtues arising from or that kind of addressed volume in the intelligence cycle, like kind of sorting through the massive data, like now you have fragmentation. So it makes it even more challenging because to sort through the data and like make clear what's valuable, what's important, and like focus in with a careful eye because the data is not integratable. It also creates bottlenecks that delay information dissemination because, again, you're having to sort through a lot of this information because it's fragmented and redundant. It makes it just that much more challenging to sort through. And also the data in silos are typically housed in formats that are incompatible with other silos, which is, again, just manifestation of the variety issue. They're also leveraged in inconsistent standards that undermine cross-data validation. So you want like that example I gave, recall, you want to like compare image versus ground troop description. Of course, the example I gave, I'm sure you were imagining looking at a picture and reading text, but don't we want to have machines help us do that sort of thing? Well, they're not going to be able to do that sort of thing if these sorts of data are leveraging inconsistent standards. And so we're not going to be able to automate cross-data validation or even support automated cross-data validation, which is a problem because, as I said, there's a lot of data to sort through. We can't do it all on our own. Now, lastly here, all of this hinders the value obtained by integrating these diverse data sets. So all together, like one of the points of the intelligence cycle is to take the raw data, figure out a way to generate useful, valuable information out of it, right? Like this is the point of the cycle. But information silos get in the way of every step, every aspect of that cycle. And so because of that, the ultimate goal of extracting valuable raw information, i.e. intelligence, out of the cycle is undermined. These are particularly problematic. And if left unaddressed, integrating disparate data will continue as it has in the past to fall on the shoulders of humans. Now, I want to emphasize this point, the disintegration, the stitching together, what we would do is we would have data that's in all-in-one format and we know it's trustworthy and we can just use that. When we don't have that, but the second best thing we could do is have it in seeming somewhat reasonable formats that can be integrated together with automated solutions, not necessarily stitched together manually, but some way that computers can assist us in a scalable way, as we work through all these large monumental amounts of data that minimizes the role that humans have to play in it. But currently, the state of the game is almost the worst case scenario where every single step of almost every single part of this process involves humans coming in and having to integrate the data by hand. And this happens so often, it's almost laughable. It's a little Sisyphean and comical, honestly, but we can do better. We can do better. And if you're thinking, oh, John, well, listen, you said, programmers can come in and stitch that stuff together. Again, those solutions that they stitch together between data sets, they're not scalable solutions. Like, you can't use it again. You have to come up with another mapping. Like, and mappings are challenging to create. Okay, so like, enough of the doomsday talk, though. Fortunately, there are long-standing strategies for addressing interoperability problems, and in doing so, support the intelligence cycle. And that brings us to ontology engineering. Now, ontologies, formally well-defined, machine-interpretable control vocabularies designed to represent entities and logical relationships among them. What they do, what ontologies are for, is to make explicit the implicit meanings buried in data sets by using basic principles of formal logic. It's really that simple. And in doing so, they provide a semantic layer that connects information silos. It's a layer that is, again, implicit across, and for humans it's not that challenging to see, but implicit across information silos. The sort of thing that whoever coded these locally silos didn't think to add into the data, but it's also the sort of thing that you have to make explicit if you're going to leverage machines. Because machines, as I've said again and again, are dumb, and they do exactly what you tell them and no more. You have to make what's implicit explicit for them so that we can leverage them. Ontology engineering has historically been a way to provide a common language across silos, and in doing so reduce fragmentation and redundancy. It also promotes automated data integration and standardizing queries, and helps standardize, or at least approach standardization for mappings which address other aspects of the big data problem. They exhibit standardized syntax and semantics and common formats and standards like the web ontology language OWL. They also have representations that leverage both textual and logical definitions that support consistency, checking, and meaning across silos. And they lastly facilitate information extraction across disparate data. And in doing so, this, again, the goal of the intelligence cycle is to find that valuable information. Well, ontologies are a way in addressing silos to help facilitate that information extraction across various disparate data sets and integrate them so that value can be obtained. Now, I just want to get ahead of this. There are groups out in the world, there are people like this guy I pick on quite a bit, unfortunately, who point out or try to make the case that knowledge graphs, i.e. ontologies with data, are rather easy to make, right? They're just easy to construct. You can do it in an afternoon. I want to be careful here because I want to make it clear that it's really easy to just create another information silo. And if you go in and follow the advice in this Medium article, or a lot of advice that you see online in Medium, you're going to end up creating information silos because you're not following a strategy that you can trust to make sure that there is integration across disparate data sets. Everybody wants to come up with their own ontology. Everybody. And guess what? That's a great way to generate a lot of silos. So constructing an ontology, if you're following one of those, maybe the gut reaction strategy that you see in Medium, can be easy. You just write some Python, read a file, generate classes and relations from column headers, or just your control vocabulary with logical relations. Easy peasy. It's also much more challenging, though, to construct an ontology according to a standard that exists, i.e. another ontology. But that is how we avoid, or at least start to avoid or address information silos. Here's a good place to start. Basic formal ontology. It is a standard, a widely used standard, probably the most, or at least among the most widely used standards in the ontology community, certainly the most widely used top-level ontology. It's used by over 700 open source groups. It was the first ISO IEC top-level ontology standard, and it is a baseline standard for DoD IC ontology development, which again makes it a rather natural choice when we're talking about supporting the intelligence cycle and analysts who use it. A snapshot here of some of the users. This is on a user page for BFO. Feel free to go check it out. Barry and I painstakingly keep this thing updated. Currently, again, over 700 projects using it just in the open space. They're more in the closed space I cannot talk about, but reference here to the ISO IEC standard 218382, and also a memorandum mandating the use of BFO and one of its extensions, which we'll meet in just a moment, as baseline standard for formal DoD and IC ontology development. What, though, is BFO? Well, you're looking at a diagram here of it, just a picture, right? It's got a bunch of classes that are represented with these rectangles. Now, classes, as we understand, represent collections of instances of things. For example, the class of tables falls under the class of objects. It would fall under, on this far left side, it would be a subclass of objects, and your dinner table would be an instance of the class of tables. Now, it's as a heuristic for you to keep this distinction between classes and instance in mind, just note that instances are things that cannot repeat, but classes have repetitions under them, right? There are many tables in the world, but there is only one your dinner table. There are perhaps many types of your dinner table that you could say purchased on IKEA or from IKEA or whatnot, but the one sitting at your dinner, or that you put dinner on, the one you're eating off of, there's only one of that. Just like there's only one of you. You are unique in that sense. You are one thing, and you fall under the class presumably human, although if I wanted to really future-proof this, I'll say organism or something like that. Who knows what's going to happen. But listen, the point is, if you can repeat something, if something can be repeated, usually that is a class. You're speaking at the class level, and there's your heuristic. And if you can't, then you're often talking about an instance. Now, I say here up in the top right, class A is a class B, and I'm referencing here in the legend, you see these arrows, these are connecting classes to other classes. And what this means, though, is that when you say class A is a class B, it just means that any instance of class A is also an instance of class B, so very similar to subset relations. So as you can see here, there is object on the far left. It is a material entity, which is to say that any instance of object is an instance of material entity. And just so you have like an idea in mind, an object is a material entity that has boundaries that connect its parts together, while a material entity is an independent continuate, that is a thing that doesn't depend on anything else for its existence, but a material entity an independent continuate that has material parts, like a table or you. So I will, at various points, touch on subtle aspects of basic formal ontology as we proceed through the course, but I do want to step back and just point to some of its methodological convictions. In particular, I want to start with realism. This is one of the things that separates basic formal ontology from other top-level ontology standards, and it's an important thing to point out. So BFO is designed to represent the world rather than just concepts about them. Then there are other ontologies out in the world that aim at representing concepts, and that's fine. When we talk about modeling the world, we also represent concepts, and we have space to do so because concepts are part of the world. And so, but we don't want to bottleneck ourselves into just representing concepts because we also want an external arbiter to some extent, namely the world, which is out there and independent of our concepts and what we think about it. We want to model that as well to the extent we can. Now, one way of thinking about this is through directions of fit for ontology engineering. And just to get the intuition off the ground, there are two that we'll have in mind here. One is word-to-word direction of fit. This is where you're trying to make the world fit words. The other is word-to-world direction of fit, where you're trying to make words fit the world. So if you're thinking of, to have this slang or solidify these concepts, so suppose you're a spy watching someone shop in a grocery store. Now suppose they have a shopping list and they're checking items off as they proceed or put them into the basket. Now you are just recording this behavior. Word-to-world direction of fit. Now suppose this person you're watching buys butter when the list directed purchasing margarine. Correcting this mistake for the purchaser would involve him buying butter rather than changing the list that he's reading off of to margarine, right? In this case, he's making the world fit the words on the page, right? On the other hand, if you're recording that he bought butter when he actually bought margarine, correcting that mistake would involve you updating your record rather than getting him to buy butter. And that's making the words fit the world. Now, I say these are two ways to distinguish sort of strategies through ontological engineering, and I've talked a little bit about realism, but let me say more about the contrast, which is conceptualism. I understand conceptualism using this direction of fit language as making the world fit the words rather than realism where it makes the words fit the world. So what do I mean though by conceptualism? So this sort of strategy in ontology and engineering it's got its start way back in 92 with Tom Gruber, who gave one of the first definitions of ontology. He calls an ontology a specification of a conceptualization. So basically what this has been taken to mean is like a really formal characterization of concepts that you have. Now, later in 2009, he said he took a more pragmatic view, and he said that ontologies are tools and products of engineering, and therefore they're defined by the uses they're put to, which has been interpreted as claiming that ontologies represent just what they need to represent, concepts or otherwise. Now, but these are the origins of this kind of conceptualist move, like thinking about modeling just our concepts rather than the world. Now, the reason me and the BFO circles take the realist route is partly on that like, kind of the philosophical ground of us trying to be able to model the world, and also we want to model concepts and not just one of the two. We want kind of a bigger boat, but also it's born out of this observation. It's very practical, to my mind, observation, which is if we attempt to go modeling from the words we use to the world, it is unlikely that we will end up in the same place. If I asked you all independently to just write down your best definition of the word facility or your concept of the word of facility, I suspect that we would get many different characterizations of facility. In fact, I'm highly confident that we would. Now, if we started from that point, what we would end up doing is trying to argue with one another about which one was the right characterization of facility. And it's unlikely we'll end up in the same place, and there's going to be a lot of blood, sweat, and tears of us trying to get there. On the other hand, if we attempt to go from the world, just trying to model the core, like basic characteristics of like facility, and from there derive the ways we talk about facilities in our own idiolects, it's much more likely that we'll remain coordinated and much more likely we'll stay in the same place. Now, this is an exercise. You can take this as an empirical like hypothesis, but it's one been borne out several times with several sponsors and several subject matter experts in my life. It's one that we will practice in this class. We will work through exercises where we do just this, and you will see the benefit of having, hopefully you'll see the practical benefit of having like an external arbiter, i.e. the world, helping like keep us with that North Star, so we're not just modeling how we talk about things, but instead trying to derive the way we talk about things from a common model. Another methodological conviction that underwrites BFO is adequatism. So BFO is not reductive. So classes and relations are motivated by research communities, and they're not paraphrased away. We're not trying to reduce this thing to that thing whenever we're modeling in BFO. We want to allow for this big boat so we can give researchers exactly what they need when they need to talk about the world. Here, and this will just kind of highlight some of the details of what I mean while also illustrating some aspects of BFO. You see here on the bottom left corner of your screen, this is Barry Smith, who is the inventor of BFO. He's an instance. There's just one of him. He's unique, right? Just one instance of Barry, and he's an instance of the class agent. Now, agent is, roughly speaking, an agent is an object that can engage in intentional actions. Now, an agent, as you see in the bubbles here, or reflected in the bubbles, is a subclass of objects. And objects, of course, a subclass of material entity. And here, again, just illustrating that Barry is an instance of agent. Now, Barry is also the SUNY Distinguished Professor of Philosophy in the Julian Park Chair. So he has a professor role. Now, this is a feature of him that is, kind of not exactly dependent on his material structure, as it were, insofar as if he were to lose the role or gain a different role. Nothing about him materially would change. It's just sort of something he can step into and step out of, but depending on the context. Now, we want to represent that instance of role, that SUNY Distinguished Professor role, as falling within our hierarchies in our ontological representations. And so we have like this class professor role that would allow us to say this is an instance of that role, and that professor role is a subclass of the broader classes of roles that include things like employee role or employer role. And all of these are subclasses of realizable entities which include other sorts of subclasses themselves, like dispositions, which are kind of modal features of objects, like solubility of salt, that do depend on their material structure. But again, putting all that aside, like the main point here, the through line is that we want to be able to represent not just the instances, but also these various properties that hang off of the instance. And we also want to represent the relationship between the instances falling under these classes. And so bearer of is a property or relation that we use in our ontological representations that link instances like Barry to instances of things like roles. And so Barry is said to bear that role. And again, as I've said, we need to make these things very explicit because, say it with me, computers are dumb and they do exactly what you tell them. They would not be able to tease out, just because there was a role and just because there was an agent, that there was some bearer of it, unless we tell them. So we allow for this. We're not trying to reduce it away or paraphrase it away. We want this information to be represented explicitly in our machine readable artifacts. Okay, lastly, so fallibilism, another one of the characteristics that distinguishes BFO from other ontologies. So BFO is committed to tracking scientific research, or the best research we have over time, and that may change. That's sort of how we get our hook into the world. Like, I'm not a virologist, but I read virology work and I talk to subject matter experts when I'm modeling viruses. And the best research at the time, like that's the one I go with. There are people who study this stuff for a living, and I take them very seriously. I defer to their expertise. And so I try to model what they're doing and how they're doing it, and as best I can, while keeping an eye on putting it under a common structure within BFO. Now, because science changes, that means we should be open to allowing for our ontologies to change and our representations to change over time as well, and we do, which is one of the reasons, incidentally, why we build our ontologies under the web ontology language, OWL, which adopts the open world assumption, which is to say that just because you have not said something in your model doesn't mean it's false. I know when I say that, you're probably thinking to yourself, well, of course, surely every language allows for that sort of. Not so. In like first order logic, for instance, which is a very common logic, they're common representation language that's used across the sciences. If you don't say something, it's assumed to be false. That is the closed world assumption. Again, we take the other tactic partly because we are fallibilist, as many ontologists are, but we take it as like a methodological conviction that we keep in mind when we're modeling, whether it's in OWL or other languages, that we are tracking scientific research that may change, and we are not trying to say that we've nailed it at any given time. So BFO, used as a top-level architecture, is rather weak. It has high-level terms like process and history, immaterial entity. Like, where do you see this stuff and farther down in the world when you're really representing stuff? Not very often, but it's designed to be extended into more specific areas and domains that cover things like livers and food and computers. And we have strategies for such extension. We don't just want to leave it up to the devices of developers. We want to provide guidance on how exactly you can extend and still align and conform with the top-level ontology that you're seeing before you. And the way, what we call this is a hub and spoke strategy. You see BFO right there in the center. What we have is ontologies that extend down from BFO as modules in this larger hub and spoke structure. And they populate downwards where new classes have parent classes in the hierarchy that ultimately lead all the way up through a backbone into BFO. And this is a way that we can create guardrails for promoting alignment between ontologies and representing nearby domains, and also progress towards interoperability by following sort of shared spoke semantics with the same hub. Now, here's an example. As I mentioned earlier, Common Core Ontology is an extension down from BFO, also one of those standards that are directed for use across the DoD and IC. Now, Common Core Ontologies itself consists of several modules, as you see here in dark blue, like an event ontology, an agent ontology, artifact ontology. And what they do is they extend down from BFO in more specific content. So more specific stuff about geospatial regions, or more specific stuff about time. In BFO, if you recall, you saw a class or two representing temporal regions or time intervals and stuff. And it's kind of really high level. But if you wanted to talk about like specific days or a day or what a day is or a week or in like iterations of days over time or cycles, that's when you would delve down into that more specified time ontology content. Same with artifacts ontology. So we in BFO provide like the high level structure for objects under which you will find things like artifacts, like bowls or knives or things like this, items that are developed or created to have some purpose. This is stuff that you would find in Common Core, but you wouldn't find in really high-level ontology like basic form ontology. Now, the analogy I like to present here between like the basic form ontology and its extensions is that they're very similar to like Python and its libraries. So I think of BFO as analogous to Python, and extensions of BFO like the Common Core ontology as analogous to Python libraries. So you could go create code that allows you to interact with like data frames, etc., or you could just start with Python and import a library like pandas. And why wouldn't you? Who wants to write there? I mean, some people do, but like I would just import pandas. Similarly, you could create ontology elements that allow you to model artifacts and processes, etc. Or you could instead start with BFO and import a library like CCO so you can start closer down on the ground. Okay, so how does this work in a little more detail? Let's look at an example. We'll work through this. So look at the agent ontology. Agent ontology, again, ultimately extends down from basic formal ontology. Now, basic form ontology, if you recall, has material entity in it. That's one of its classes. A material entity has matter as parts, right? It's an independent continuance, and they have material parts. It's in BFO. If you drop down to the agent ontology, if you combine the agent ontology with BFO in an editor like Protege, which is sort of a screenshot of what you'd see here on the left, you can see that agent, that class, would fall under the material entity class in BFO. Now, agent is part of the agent ontology. It's part of the Common Core suite. Now, what's this connection, though? So we follow a specific strategy for creating classes and subclasses like this, where the definition of ontology elements are created following a recipe to ensure that the hub semantics are preserved by the spokes, and in doing so, minimize human error. So here are the definitions. Just again, material entity is an independent continuant that has some portion of matter as part, and an agent is a material entity that's capable of performing intentional acts. Now, the strategy that we follow, though, is leveraging this A is a B that C's recipe, where A is the thing you're defining, and B is the parent class under which A falls. Here you'll see the parent class of material entity is independent continuant, so that's in BFO. But if you focus here for CCO proper, you'll see that agent A is a material entity B, and that material entity is, as you can see, right there in its parent. So we have this sort of genus-species relationship where you're always pointing back to a parent that's above you in the subclass relation. And then we have the C's, and the C's here are the whatever content you need to differentiate all of the other, or whatever A is from all the other B's that are like sibling classes, right? So how is agent, you can think of how is agent distinguished from all the other material entities that are subclasses of material entity, like tables, for instance. You could have a class of material entities that are tables. And presumably, unless this is some weird fever dream that I'm waking up from, tables do not engage in intentional acts. Agents do. There's a differentiator that distinguishes them. Now, again, this hub and spoke strategy provides guardrails for promoting alignment between ontologies representing nearby and overlapping domains. And by following the recipe, progress towards interoperability is promoted up front, since some elements inherited from the hubs overlap semantically with one another. Now, again, I want to emphasize the importance of this approach in addressing silos. So if you don't follow this strategy, it's very likely that you're going to get silos. I'll give you an example. Over here on the left, you see the Credential Transparency Description Language, CTDL. It covers credentials. It's a very extensive list of credentials. It has things like degrees, diplomas, doctoral degrees. It's really cool. It's really useful, and it's really widely used, especially in Alabama. Their Alabama Talent Triad is leveraging the content they see from CTDL in some of their larger architectures. As you can see, though, OntoB, which is a repository where you can like go look and search through different ontology content, like that's just stored in-house from various sources. You see that like there are terms, there are definitions, there are like there are like classes already represented in OntoB that are, say, credentials or diplomas. Those classes on the right-hand side, the ones that under OntoB, those are from the occupation ontology, and it's built on top of BFO. It actually has a top-level ontology. The ones over to the left in CTDL, characteristic of them, they do not have a top-level ontology in common. They don't have some like overarching high-level semantic content that can bridge them to others. And because of that, or other information repositories, and because of that, they're effectively siloed. Now, this is a consequence of this that may not have been obvious up until now. So I was talking a lot about siloing and the impact that it has, and like having to stitch together databases or information systems, the sort of consequences it has monetarily, as the NIST and McKinsey studies show. But look, here's another consequence. I just want to point this out and highlight it. It's a very important one. So hub and spoke strategy, as we practice it, significantly cuts down on what we call scope creep, which arises when ontology is created as an information silo, but over time grows beyond its initial scope. Now, if the ontology does not extend from a higher level ontology, it will likely not be compatible with other ontologies. You just saw an example of this. CTDL has content that the occupation ontology has, but there's no like clear way to connect them together. They were developed independently. Best case scenario, you have to stitch them together, writing code and with mappings and the sort that I was describing earlier that we're trying to avoid. Now, if CTDL or any other information silo grows beyond its initial scope, what happens is they often need to recreate existing work that they can't interoperate with. And an example is right here in front of you on the very bottom of the list. This is a credential transparency description language, and yet they have a class for geocoordinates. There are many geospatial ontologies. There's this Common Core ontology, geospatial ontologies. They could leverage content from that if they needed to represent that. Well, at least, in the abstract they could. But because they were created with no top-level semantics, no way to connect to these other representations, there's no easy way for them to do this sort of work. And so because they need to move at the speed of mission, needing to satisfy their customers, etc., what do? They go create content that already exists and just dig themselves further and further down into this siloing effort. Now, ultimately, if they did all of this and they continued to do it and they had their grand schemes and all of their druthers, they'd just recreate the world, right? But again, everybody else would too. This is, again, a consequence of siloing. If they just had a common semantics, then we can integrate more easily. We can use automated methods to do so, and we wouldn't have to do what I think we're going to have to do in the future, which is argue about whether they should keep geocoordinates as a class, drop it, or integrate it with others, or connect it with others, which is just a mess. So with that, I just want to close and say we've covered a lot of ground, but hopefully you get the idea. The intelligence cycle has a lot of virtues associated with it. It also runs into problems that many other information systems or strategies for getting like vettable or high quality value out of raw data encounter, which is this problem of information silos. Now, there are known strategies, decades-long strategies for addressing siloing, and they're becoming more and more popular. Among them is the basic formal ontology, which is very much relevant, especially in the DoD and IC circles, to modeling intelligence information. Now, I discussed how BFO, alongside its methodological convictions and like implementation strategies, can go some way to addressing information silos, and in doing so, highlighted again some other consequences that occur downstream when folks create information silos that exhibit what we're calling here scope creep. So, but again, ultimately, hopefully the value and the virtues to the intelligence cycle and beyond of starting with an eye towards addressing information silos is clear, and we will keep that in mind as we progress through the rest of the course.